Let me begin in terms of session 3. Session 3 is about economic growth and the way forward. We've had a good morning with a number of thought-provoking presentations, and our last session has key speakers from industries in each of the three sectors in terms of water, agriculture and energy, focusing on what's practically needed to manage the Nexus. The first of our speakers is Greg Appleby, an energy specialist at Sydney Water. He has extensive experience across Sydney Water operations, but has spent the last 5 years as energy management specialist with experience in energy procurement. Greg, thank you. Greg, thank you.
Thanks, Jamie, and thank you to the AWA for this opportunity. Today I'm going to go through examples of where energy and water link within Sydney Water and water utilities generally. And then I'm going to go through energy management practices that Sydney Water carry out. Just a brief introduction. Sydney Water provides drinking water, wastewater, recycled water and stormwater services to people within Sydney, Illawarra and the Blue Mountains. We do that by operating 5 water filtration plants, 29 treatment plants, wastewater treatment plants and 14 recycled water plants. So that's a lot of assets, a lot of energy consumed in those assets, and on top of that we've got about 1,000 pumping stations as well. So I'm going to go through, as I said, a couple of examples of where water and energy meet, link at Sydney Water. And the first example is probably the most obvious. When it rains, a lot of that water leaks into our stormwater, into our wastewater system. And there's also a lot of connections from stormwater directly into our wastewater system. So the impact that has, you can see the big blue bar there, representing a lot of rainfall in one period, and the immediate impact is a large consumption of energy. And you can see that it's taken about 4 days for that energy consumption to come back down to normal. So this graph just shows, we saw this one earlier, but it just shows that thanks to a variety of measures that Sydney Water carried out, we managed to bring water use down significantly. And this had inadvertently a significant impact on energy as well. Whoops. Phew. So you can see there water usage coming down again. And corresponding with that has been a significant drop in energy use, and that's just because pumps aren't having to pump as much water around the system. My final example is energy intensity within the Sydney region, and low energy intensity is represented by the green, the lighter green, and higher energy intensity is represented by orange and red. So you can see the area in green is around the Prospect water filtration plant, which is just around there. And so it's supplying water to areas that are in the flatter regions of Sydney, or gravity feed down towards the Sydney Basin. And so not as much energy is required to pump that water to those areas. But the areas in orange above, these are areas in orange, this area in red particularly at the top of the Blue Mountains, are quite hilly, so require a great deal more pumping, higher energy intensity. We've also got regions down here and down here that are a little bit more orange, and that's because there's some more smaller, more inefficient water filtration plants. This area over here contains our desalination plant. You can see in that blue box to the right that has a higher energy intensity than any of the other methods for bringing water to taps. And when that's mothballed at the moment, but when that's turned on, this whole area will be red. So how do we manage our energy cost? First of all, we have an electricity bill of around 49 million a year. That's been increasing, so energy is forefront in Sydney Water's mind. Energy cost is a function of the price we pay per unit of energy times by the volume that we consume. So those are the two areas we focus on. How do we manage cost? We've entered a flexible procurement agreement with our energy retailer, and what that means is that we can purchase small blocks of energy when we consider prices a fair value. We can purchase larger blocks when we think we're getting really good value. And this has led to lower electricity costs for Sydney Water overall. We also have an energy efficiency program that helps us reduce our volume, and on top of that we've got a renewable energy program that also helps us reduce our volume. I'll go into both of those shortly. So Sydney Water has a target to maintain energy use below the levels in 1998. That's grid purchased electricity use, and you can see the dotted line here, that's where we're up to now, and this green bit represents the energy that is being produced by renewable energy, and the bit in purple is the energy that we're saving in terms of energy efficiency. So if we didn't implement both of these programs, we'd be up here around about 450,000 megawatt hours a year. And if we go to the future over here, the orange bit represents the energy that we intend to save in the future to maintain our electricity consumption below 98 levels. So that's going to involve further energy efficiency projects and further renewable projects as well. So this pie chart represents the electricity breakdown for Sydney Water. You can see the larger piece of pie there is wastewater treatment. That consumes half our electricity consumption. The bit in green represents water pumping. So those areas are obviously where we're going to concentrate our efforts when we're looking at energy efficiency and renewable energy. Pie chart down the bottom describes the percentage of renewable energy that we are producing compared to what we're purchasing from the grid, and you can see there that 14% of our electricity usage comes from renewable sources. We also export a further 2%, and we try and limit our exports of electricity because we don't get as good a value as if we offset the electricity that we're purchasing. So in order to carry out energy efficiency projects, we have an energy efficiency management program. We have $1 million a year to spend on energy efficiency, demand management and small-scale renewable projects. But each of these projects within that $1 million must have a positive NPV, and they must take into account the risk of increasing costs, of increased costs of implementation and or decreased revenue. We also have managed to save 3.3 million, so it's been quite a successful program over the last 4 or 5 years. So I'm going to give a couple of examples now of how we save energy in pump stations, because this is obviously a relevant topic given the Energy Water Nexus. So the first example has to do with load shifting, where we stop pumping during peak periods between 1 or 2 p.m. to 8 p.m, and we shift that load to off-peak and shoulder periods. That saves us cost thanks to the higher time of use cost during peak periods, but it also saves peak demand charge. Another way to look at energy efficiency of pumps is to look at the specific energy of pumps against flow. Here you can see that the pump is going to operate inefficiently if we send flows through at 20 litres a second, or much more efficiently if we send flows through of more than 40 litres a second. You can also use this. Some pump stations have pumps of different sizes or energy efficiencies, and so you can use this chart to determine which pump you're going to use at certain flows. So I've talked about pumps. Now I'm going to talk about wastewater treatment. Some of the energy efficiency projects that we carry out at treatment plants are quite simple, like replacing fluoros with LEDs. We also do temperature control of switch rooms, but it moves to the more complex, like some of the aeration projects which require SCADA controls or replacing blowers or installing VSDs as well. Renewable generation, we carry out three types of renewable projects: hydro, biogas generation, and solar. We have 2 hydro facilities in pipelines, water pipelines, and 1 in the wastewater treatment, where we use gravity flow from our North Head effluent. Biogas is, I'll just give you a bit of background on biogas. When you treat sewage, you end up with sludge. If you place that sludge into digesters and treat that anaerobically, the product is biogas, and you can then use that as fuel, which it contains about 65% methane. You can use that as fuel for engines with generators, and you can generate electricity. And that's called cogeneration. We also have a very small solar system. You can see that on the roof of the building just there, and that's about 60 kilowatts. But moving forward, we're going to roll out some more solar. We've got about 100 kilowatts approved. We're going to roll out to smaller sites that have higher tariffs. We're also looking into mini and micro hydro, some wind, and we're also looking to improve our biogas generation by optimising some of our existing processes. But we're also looking at co-digestion, which involves adding food waste or other materials to our anaerobic digesters, and we think we can double our biogas at certain treatment plants. And by doing that, we're hoping to make some of our wastewater treatment plants self-sufficient. So at Bondi, we're about 90% self-sufficient. With co-digestion there, we believe we can make it 100% self-sufficient. And importantly for us, renewables are only cost-effective behind the meter. So what that means is if you export electricity, as I said, you don't get good value for your money. But if you use all that electricity on site and offset grid purchases, then you're going to make better value for your money. So this diagram represents the asset cycle and where we intend to play within that. So far, I've described energy efficiency projects that involve retrofit. We're looking to get involved in the planning, design, renewals, maintenance areas. So for example, a very simple example is getting maintenance teams to replace broken fluoros with LEDs. So we have a strategy for each of those areas that we intend to carry out shortly. So energy efficiency and renewable projects have significant barriers. We work through those barriers, but some of them are very difficult to overcome, like our tariff structures at some of our sites. Some sites have tariffs that are electricity tariffs that are loaded more with fixed costs, and it's very difficult to get energy efficiency projects or renewable projects over the line if it includes fixed costs. Also, obviously, cost to implement, and some electricity network providers provide demand-side abatement programs, but those are too small to warrant us changing the way we manage our sites. There's also barriers to renewables. I've gone through a few of these already. Export I've gone through. Tariff is the same deal. Costs to implement, particularly relevant with solar, where previously we couldn't implement solar because it was too expensive. But as the years have gone by, solar's come down, and to the point now where many sites are cost effective. Cost to maintain for cogeneration. Many of our, where we have cogeneration, it's very costly to maintain, so we're looking at other options for our biogas. And finally, small-scale cogeneration sites are not cost-effective. We found that sites that receive flows of below about 20 megalitres a day aren't cost-effective for cogeneration. So unfortunately, we have to flare all our biogas at those sites. In summary, water supply and treatment is very energy intensive, but we have an energy efficiency program and renewable programs that help us offset those costs. And we're looking to address energy at the planning, design, maintenance, renewals stages of the asset cycle. There's significant barriers to energy efficiency and renewables, but we're working through those. Thank you very much.
Greg, thank you. Fantastic presentation showing some of the challenges, but what's possible with a bit of dedication.